quantum states with single qubit measurements. Stage is yours, Robert.
Yeah, thank you so much for the introduction. I'm Robert. Actually, right now I'm at Google and MIT. I was at Caltech before. And yeah, today I'll be talking about certifying almost all quantum states with few single qubit measurement. This is a joint work with John Preskill and Mehdi Salomanifer. We know that quantum systems with intricate entanglement is very important in quantum information science. It's being used for doing classically hard computation, for sensing about things, getting advantage, and also for quantum communication. And in order to create these quantum systems with intricate entanglement, it is important to understand, it's quite hard experimentally to create them. And oftentimes there's going to be noise and errors that happens in experimental devices. And hence, when we try to create such quantum system in the lab, we would like to really check whether the system that we have created really is the target system we would like to create. And in order to do so, we need to perform certification. So for people that doesn't know what certification is, it's the following very simple task. We have some desired n-qubit state psi, which is our target state. We would like to realize them in the lab because such state might be useful for sensing, for communication, or for doing simulation, etc. On the other hand, in the experimental lab, we're going to create some density matrix rho, an n-qubit state that might be close to psi if we did a good job, or it might be far away from psi if there are some uncontrolled errors. So the certification task is the following task, which is we would like to perform measurement on the lab state rho, such that from the measurement data, we would like to test whether rho is actually close to the target state psi or not. So if it is close, we say we certify it, and if it's far, we say, no, this is far. Particularly, the closeness is often defined based on fidelity. And the fidelity expression is just psi rho psi. We just try to check whether psi rho psi is close to 1 or if it's far from 1. If it's close to 1, we say it's certified. We say it's close. If it's far from 1, then we say it's not good. So there have been tons of work for doing certification. There's a lot of different proposals and techniques for doing certification because it's a very important basic task. For example, Adam Shah and Soon-Won Choi's talk yesterday were essentially also proposing different ways to understand algorithms for doing certification. However, so the full certification task, as I stated earlier, it's still experimentally quite challenging to really establish this task. And to showcase that, I would go through a few methods, like more commonly used methods that people are being considered in the lab. And as a starting point, I would talk about approach 0. It's not really an approach that people use, but it's like a very simple approach that one could think about. It's just direct measurement. So say your target state psi can be created by applying some deep quantum circuit U onto the all-0 state. Then one kind of theoretical proposal for doing certification is, given a lab state rho, which is the quantum state on the left, we just implement U dagger, and then we do single qubit measurements. They measure everything in the Z basis and check if we get all 0. But this definitely works, but it works under the assumption that we can implement U dagger perfectly. So the key challenge is that if we assume that we can implement U dagger perfectly, then we should also be able to implement U perfectly. And in this case, rho can be created to be arbitrarily close to psi. And hence, if this is indeed the case, if we live in this world where we can implement U dagger perfectly, then there's no need to do any certification. And hence, this approach kind of doesn't work because of this. Another approach that have been considered for existing devices was based on randomized Clifford measurement. So instead of implementing U dagger, which can be, say, very deep if the circuit has high complexity, instead we just take the quantum state in the lab, implement a random Clifford circuit onto it, and then measure in the Z basis. So after doing that, using classical shadow formalism, one would be able to collect these measurement data to predict the fidelity between the lab state rho and any rank 1 state. So in this case, we will be able to estimate the fidelity directly, and then from there we can do certification. However, this approach also has a lot of challenges, which is it requires running this deep random Clifford circuit on the lab state rho. So as we know, like running a depth-n circuit for say n about like a few hundred qubit is still experimentally very challenging, and it's quite hard to do so. And hence, this approach is also not that satisfying. Yeah.
Does this approach work for any input state?
Yeah.
Okay.
For any row and any target state psi, one would be able to run a small number of measurements and be able to estimate psi row psi. So this approach. Alternatively, instead of implementing a deep Clifford circuit, we can also just measure all the qubits in a random Pauli basis. So that's called random Pauli measurement. And again, using classical shadow formalism, one would be able to also predict fidelity. But the challenge for this approach is that now, while it only requires single qubit measurement, it doesn't require running these deep circuits, which are experimentally challenging to implement. For estimating some highly entangled target state psi, this would require performing an exponential number of measurements, since this is just doing like randomized local measurement. And from there, all one can estimate efficiently are local reduced density matrices. And the scaling grows exponentially if we wanted to consider more global observable, such as the target state psi. And hence, this is also not a very satisfying approach if we wanted to certify highly entangled quantum states. The third approach that have also been considered in many different scenarios is by doing cross-entropy benchmarking. So here, this is even simpler than randomized Pauli measurement, because instead of measuring every qubit in a random Pauli basis, we just measure everything in the Z basis. And then from the measurement bitstring data, we estimate the XEB score. And if we see that the XEB score looks good, like it's the normalized one, if it's close to 1, then we say it's good. And if it's far from 1, we say it's bad. This approach definitely has this advantage that it only requires Z basis single qubit measurement, so the cheapest among all of the approaches that I talked about. But the challenge is that it cannot rigorously address the certification task because it only looks at the Z basis. So if there's error that happens in the off-diagonal elements of the density matrix row, this approach will never be able to see it. And hence, if we get a perfect cross-entropy benchmarking score, the state in the lab can still be very far away from the target state site. So these are just a few of the more common methods, but there's definitely various other, like direct fidelity estimation from Steve Lamia and others, that allows one to efficiently estimate or efficiently certify certain class of states. And there are definitely also several other variants of it. But all of the existing certification protocol either require running these deep quantum circuit before the measurement, or if it doesn't require running deep circuit, it requires using exponentially many measurements. Or if it's efficient, it only works for some specialized target state, like say matrix product state or PAPS, or some other one, like stabilizer states. Or maybe it works for a lot of different target state, but like XCB, it's believed to work quite well for chaotic target state, but it lacks full rigorous guarantee because we know like it only measures Z basis.
Do you care about like computational efficiency, or is just you're assuming that you can perform whatever computation you want afterwards?
That's a good question. Right now, the thing I talked about are not, for example, XCB. It's not computationally efficient. So right now I'm mostly focusing on measurement, but the protocol that I'm going to talk about, it will be efficient, as I will show in the numerical. So yeah, so from these existing challenges, it raises this main question that we would like to address in this talk, which is, can we rigorously certify highly entangled quantum state by performing only a few number of single qubit measurements?
A quick question. I mean, with 1 qubit measurements only, don't we have a tomographically complete set of measurements?
So when I say single qubit measurement, I meant
You mean you're literally only measuring
like this. Like for every qubit, we measure individually. But we can
sure,
take a
right. Yeah. But aren't there measurements of that kind that are tomographically complete?
Yeah, they did.
There are. Okay,
Randomized Pauli measurement are tomographically complete.
Oh, okay. So
but
then,
it requires exponential.
Oh, all right. But then it requires exponentially many. Okay, got it. Thanks.
So the few is important. So we don't want to run exponential number of single qubit measurement, and that's one of our goal. And more ambitiously, one could ask, like, instead of just certifying highly entangled quantum state, can we certify almost all quantum state from performing few single qubit measurement? And that's the question we're going to answer in today's talk. So the outline of the talk is I would start by talking about two theorems that we proved in this work. And then I would talk about the protocol that we constructed to showcase, to establish the theorem. And finally, I would end with a few applications. Let me begin with the theorem. So the first theorem that we show is mostly of pure theoretical interest. It says the following. It says, for almost all n-qubit state psi, we can certify whether an arbitrary lab state rho is close to psi or not, using only order n squared single qubit measurement on the lab state. And hence, essentially answering the question positively. And note that this certification procedure applies to any quantum state rho. So meaning that it will be able to detect all kinds of error. So if there's some error that appears only in the off diagonal, this method will be able to, we will be able to detect that. In contrast, for example, XCB would not be able to detect.
Can I ask a question?
Yeah.
Does almost all mean hard random?
Yeah, so here this theorem one is mostly of theoretical
But I
interest.
mean,
So
you know, if you prove something about
Yeah.
hard random states using the fact that it's hard random, you're excluding the place where you care about things, which is the corner,
yes,
when things are algorithmically interesting.
yes. So
So
there's
I
theorem
don't
two
understand.
that I would talk about. This is theorem one. This is purely of theoretical interest. It's like conceptually interesting that if you have even these hard random states that have exponentially high circuit complexity, I mean, yeah, like this holds, like order n squared is enough even when psi has exponentially high circuit complexity. So
When you say n squared, does that mean n squared measurements, each one of them of all n qubits?
yes. So yeah, so at least this is just trying to showcase that intuitively, it seems like local measurements should not be able to see highly global structure. But from this theorem, it says that actually for almost all kinds of these random looking entanglement structure, we will be able to certify them using only order n squared single qubit measurement.
Yeah, can you come up with a similar theorem for XCB2, or that's not the case?
No, not the case. Because
What is the subtlety?
the subtlety, I mean, XCB as described, like it only looks at the Z basis.
Right.
So your off diagonal could have a bunch of errors and you will not be able to see that.
Right.
Yeah.
Or you could just spoof it by just, putting all the, mass on the things that get a high score.
Yes.
So you're choosing psi to be like typical how random,
Yes.
or you choose rho to be potentially adversarial.
Adversary. Yeah. Anything.
I see. That's the rule, and this theorem holds in that rule.
Yes. So it's like, yeah. And then theorem two will talk about if I have a specific state psi, how can I certify that state? So yeah, so as Eddie pointed out, the theorem is mainly of conceptual interest because in practice, we don't care about almost all n-qubit state. We only care about, say, one particular state that's going to be useful for, say, quantum sensing or for communication or for other purposes like computation, simulation, etc. So I'm going to talk about a more specialized theorem that focuses on a specific state psi. So now let's consider a specific target state psi, not almost all, but just one. And we would like to certify this target state. So how can we do that? So first, we're going to choose some basis for the target state. One can think of the basis as maybe it's the all Z basis, or it could be the all X basis, or the all Y basis, or a mixture of them, or some other single qubit basis. So for each qubit, we just choose some basis, like locally choose a direction, and we define a basis. And now after we pick the basis, so note that there's this freedom that one could pick this basis. After we pick the basis, it would induce a measurement distribution, pi of b, corresponding to measuring the target state psi under that basis. So it generates some probability distribution according to the basis. So for example, if it's a GHZ state, if we measure in the Z basis, the distribution would just be all 0 and all 1. But if we measure in the all X basis, now it will be a pretty uniform looking distribution, where it's supported only on, say, like parity 1 bit strings. So now we can visualize this measurement distribution as a distribution over the Boolean hypercube. So here it's just a 3-bit Boolean hypercube just to showcase it. And now I'm going to show that certification task actually is closely related to a random walk on this Boolean hypercube. And the random walk is defined as follows. So let's say we're at a certain point, a point bitstream B. Let's say right now it's 0, 1, 0. The random walk is defined, it's basically a standard random walk, but the random walk is more precisely defined as follows. At this point B, we will randomly pick one of its neighbor. For example, we pick B prime. So uniformly randomly, there's only like n neighbors, we pick one of them. And then we're going to decide whether I'm going to stay at B or I'm going to jump to B prime. And the probability for staying and jumping is basically the following. With probability proportional to pi of B, I would stay. And with probability proportional to pi of B prime, I would jump. And that's it. So that's the random walk that I'm going to consider. So for example, if the distribution over the Boolean hypercube is pretty spread out and well connected, then this random walk could mix very quickly. For example, in GHZ state, if we look at the Z basis, that would not mix very quickly. But if we look at the OX basis, that would mix very quickly. I mean, in that case, we need to consider like not just jumping to distance 1 neighbor, but distance 2 neighbor. And one could do that. Basically, we define tau to be the time that is required for the random walk to relax to the stationary distribution pi. Yeah. So usually, I think the formal way people define it is like, suppose you start out with a point that's sampled from the distribution pi, but think of it as a single point. And so it's a kind of a point distribution. And now after doing random walk, it would start growing. And the time is essentially the time it takes to be like smaller than some, like to be a small constant far away from the true pi. So there's no epsilon needed, it's just a small constant. I mean, that's the standard definition for mixing time. And now with the notion of mixing time, basically we can state theorem 2. So if we are given some n-qubit state psi, and we have cleverly chose a basis, such that it has relaxation time, say, tau, then we will be able to certify if an arbitrary lab state rho is close to the target state psi or not from order tau single qubit measurements. In particular, one can show that for almost all quantum state psi, its relaxation time is bounded by order n squared, and that's how we get theorem 1.
So when you say for almost all, do you mean high probability or
Yes. Actually, it's like with except for only an exponentially small corner.
Okay. So
It will.
because almost all would be like stronger.
Yeah. Not yes. With high probability. So not the almost all in the.
And maybe I missed this, but you now said the relaxation time of the state, but just you were talking about the basis, right?
Yes. So it's a relaxation time, like given a state, and then we look at a specific basis, it induces a classical probability distribution,
Right.
and it's just a relaxation time of that
So
probability.
in this theorem, what's the basis?
Oh, so yeah, so basically you can choose whatever basis, and you would get this theorem. The single qubit measurement will depend on the basis.
Right. The measurements will depend on
Yeah. So if you can cleverly find, I mean, there could be different bases, like for GHZ state in the OZ basis and OX basis, the relaxation time is very different. Then you should choose one that's smaller.
But so when I want to decide whether the state is certifiable, I have to like search.
Yeah, have to kind of do that. Or you can just pick OZ and hope for the best.
Excuse me.
Yeah.
In all these protocols, you have only one copies of a row or?
No. I mean, every time we think of it as we can do experiments. So every time we can generate a copy of rho and then we measure. And we do that for order tau number of times.
Given a pure state psi, is it computationally efficient to find the basis as a small relaxation time?
Not very clear. not great. But for many target state that people would care about, one could often cook it up. Because usually for the state you care about, there's a lot of structure in them. And then in that case, you can just choose it. On the other hand, if you have a state that's pretty unstructured, like maybe it's a chaotic state generated by some random circuit or generated by a chaotic evolution, one would expect theorem 1 to hold. So
This based on some sort of quantum version of pseudo randomization.
oh,
So having a pseudo random implementation of this interaction.
oh, actually, the relaxation time is only used as a kind of a conceptual thing. Like the protocol never uses these random walks. It's just for the proof. The protocol is, as I would show, it's a very simple protocol that doesn't talk about any random walk. It's just some simple measurements.
Sorry, you could certify the GHC state by only making x-qubit measurements?
No, so you first pick x-qubit measurement. Maybe it will become clear when I jump to when I talk about the protocol. But essentially there you would measure everything in x, except for 1 qubit, you would measure, or 2 qubit, you would measure in a random XYZ basis.
You have to.
Yeah, one needs a little bit more than just a fixed basis in order to see the off diagonal. The one doesn't need a lot. I see, that's what I wish.
Just for like intuition, like, is this all affected the classical shadows? Like, is it true that, let's say, if I take a state and look at it in a random Clifford basis, that this like with good probability has small relaxation time?
Yes.
So could you like derive classical shadows from this?
Possibly, yes, but this proof is much more complicated than classical shadow. Okay. In particular, one can restrict to just performing Pauli basis measurement, and in that case, one would need order tau squared single qubit measurement. So let's just jump directly to.
And theorem 1 can be derived as a special case of this? Or?
Yes.
Yeah.
I mean, it requires proving another theorem that says for almost all state, like say.
Sure.
Yeah.
But and is that the simplest way you have to prove theorem 1?
Right now, that's the simplest way to.
Okay.
Okay, so let's jump to the protocol. The protocol is very, very easy. We just repeat the following randomized measurement for a few times. So we have the lab state, this quantum state, and we're going to do some single qubit measurement on it. And the way we do that, I mean, we're going to fix a basis. And now when I say z basis, I meant in that basis. So what we're going to do is we're going to randomly pick 1 qubit x. And for everything except for that 1 qubit x, we're going to measure in the z basis. And then for the 1 qubit x, we're going to measure in the random Pauli basis. And that's it for the whole protocol. And now from these measurement data, so you can see it's mostly just a bunch of bit strings, but there's also this attached information of which qubit I'm measuring in a random basis. And now from these measurement data, we will be able to perform certification. And it's essentially done as following. So the post-processing is the following. Note that the measurement outcomes on all except the x qubit, it actually specifies an edge on the Boolean hypercube. So if you cannot see it, basically you can think of it as, suppose the qubit x turns out to, if we also measure in the z basis, and it turns out to have bit 0, then we think of then the whole thing, let's say we say the whole bit string is b0, and if we got 1 here, let's say the whole bit string is b1, then b0 and b1 only differ by 1 bit, and it's the bit x. And hence, because it differed by 1 bit, it essentially specifies an edge on the Boolean hypercube. So now, from the measurement outcome on all the z-basis measurement, we can essentially think of, or have in mind, that there's going to be an ideal post-measurement 1 qubit state. So suppose the state is actually psi, and we saw that edge from the other z-basis measurement, which correspond to b0 and b1. We know that on qubit x, the ideal post-measurement state would get collapsed into a state that's proportional to this b0 psi 0 plus b1 psi 1. So the only computation that we need on classical post-processing is to be able to compute this probability amplitude, which, for example, for neural network quantum state, for tensor network, for a variety of different states, one can compute that efficiently. And computing that is very similar to like the requirement also used in cross-entropy benchmark. Like they also need to compute such quantity in order to do XCB. And then what we do next is we're going to use the randomized Pauli measurement on this 1 qubit to estimate the fidelity between the noisy 1 qubit that lives here with the ideal 1 qubit state that we got from the previous round. So that can be computed efficiently if we can compute this 1 qubit state efficiently. And after that, we just average this omega, which is the 1 qubit fidelity across different qubit, across different runs, across different measurement. When we average it, we get this expected value, which we are going to call shadow overlap. And essentially, the claim is that by looking at shadow overlap, we will be able to do certification. So note that omega is a fidelity, so it's between 0 and 1. And hence, this shadow overlap would also be a number between 0 and 1. And the claim or the intuition is that if shadow overlap is close to 1, the fidelity would be close to 1. And if shadow overlap is far from 1, the fidelity is far from 1. And to make that more precise, one can essentially prove that if shadow overlap is, say, greater than or equal to 1 minus epsilon, which is close to 1, it implies that the fidelity would also be close to 1, but subject to like a kind of a slackness that corresponds to this tau, which is the relaxation time or the mixing time of this random walk. On the other hand, if the fidelity is close to 1, it also implies that the shadow overlap will be close to 1. And hence, by looking at shadow overlap, we will be able to do certification because it can be think of as a surrogate of fidelity. Just to build more physical intuition about what shadow overlap is, here one can just write it out explicitly in terms of this form. And from this form, one can do some simple calculation. For example, if we consider the target state to be all minus and the lab state to be all plus, this has fidelity 0. And when we plug it into this definition, we will also see that the shadow overlap is 0. On the other hand, if the target state is actually all plus, but the last one is minus, and the lab state is all plus, the fidelity is still 0. On the other hand, when we plug it in, the shadow overlap would give rise to something like n minus 1 over n. And more precisely, if there's k bits that are different, k qubit that are different, the shadow overlap would be something like n minus k over n. And hence, in a way, one can think of this shadow overlap as like a Hamming distance version of fidelity. So it doesn't always match up with fidelity. It matches up in kind of a global noise regime. But when their error is only happening locally, it has a more Hamming distance flavor to it, which can be useful for certain applications. So now let's jump into the applications. So now we have this new certification protocol. What can we use it for? So the first example is kind of just by construction. We can use it to do benchmarking. Because by looking at this value shadow overlap, if it's close to 1, we can certify that the state has high fidelity. So here are some numerical experiments to compare with, say, cross-entropy benchmarking. So the first example, we look at 4-qubit hard random state under white noise. So this is a regime where cross-entropy benchmarking is expected to work. It's expected to work when the state is pretty random, and it's expected to work when there's white noise. And this is indeed what we see. So as the white noise increases, we see that the XCB tracks the true fidelity quite well. And similarly, the shadow overlap, which are these diamonds, also track the true fidelity very well. The same holds for, say, 20-qubit hard random state. One could also replace these by like a high design state rather than hard random. And now things start to change when we look at not white noise, but coherent noise. So suppose now that the target state and the lab state differ by some coherent errors. So there might be some over-rotation or under-rotation in the system. But the target state is still a hard random state. In this case, we see that the XCB start to deviate from the true fidelity. In particular, in this case, for the 4-qubit example, it underestimates the fidelity. It thought the fidelity was lower than what it should be. On the other hand, because shadow overlap allows one to look at one qubit in a random XYZ basis, it allows one to capture the errors in the phase better. And we see that it captures the true fidelity much better than XCB. On the other hand, for 20 qubit, in this case, XCB and shadow overlap both performs well.
So in the previous plot for the 4-qubit for the XCB case, did you just plug in the formula for the infinite system size, or
No.
finite dimension parameter?
Yeah, I do that right normalization.
And average over different unitaries, or?
Oh, no, this is just a single instantiation. However, the things really start to change when we don't look at hard random state, but when we look at some more structured random states. So here we look at a state which is just a product state, and then we apply some phase circuit, so like a diagonal unitary onto it. So that's our target state. In the white noise regime, we know that XCB is still going to work, and indeed we see that it's still working. It tracks the true fidelity well, but the variance is very large. On the other hand, shadow overlap has a much smaller variance. And this is the case for 20 qubit. And now, in this final case, we consider these random structure state, but subject to coherent noise. And this is really a regime that XCB is not going to work very well. And we see that as the coherent noise increases, somehow XCB scores is fluctuating a little bit upward. On the other hand, shadow overlap, it doesn't track perfectly. You can see there's still a difference between true fidelity and shadow overlap in the high noise regime, but it at least tracked the trend. And in many cases, it's quite close.
What are those error bars? You've done different instances. I mean,
Oh, no, it's just I repeat, I fix the number of measurement, and I repeat that many times.
okay.
Yeah,
The same
and then, the same state, everything the same, but just like the measurement is different. And now for the fixed number of measurement, that's the variance.
Why do we not see the error bar on the shadow overlap?
It does. It's just so small that it's like visible. Like the marker is a little bit bigger than the error bar. And this is the situation for 20 qubit. We see that the XCB is not as bad, like as in the 4-qubit case. In the 20 qubit, it's still like kind of fluctuating in a weird fashion because it's not really capturing the noise that's happening since it's only looking at Z basis. That's one way to think about it. On the other hand, shadow overlap look at almost all Z bases, but 1 qubit in a random Pauli basis. And suddenly that allows one to see a lot more about the error that's happening.
Sorry, so just to make sure, when you say coherent noise, you have a formula U phase. Does that mean you are just changing the phase just before the measurement?
No, actually, like I take psi, and I kind of sample a random unitary that's close to psi, and then I perturb. So if I only change the U phase by the phase, then it's not going to see anything. Yeah. So here I'm choosing really more like a more global random coherent error.
Yeah, did you look at some other colors of noise other than white? Did you look at like, did you look at like other noise colors?
Oh, I see. Yeah, not really, but that's definitely something. So yeah, so this is a first application for benchmarking quantum devices. Kind of, this protocol is designed for that. But there's also several other applications that one can consider. For example, there's these popular methods called neural network quantum state tomography or machine learning based tomography. The idea is that we have a quantum system in the lab, and now we would like to train a neural network to represent it efficiently. And one of the benefits of that is if we indeed do a good job in training the neural network to represent the state, the neural network can be shown to be essentially a sample and query oracle that was used in like dequantization, where from that neural network model, we will be able to predict a wide range of observable, like sparse observables, and we will be able to simulate 2-copy measurement or multi-copy measurement from them. So there are quite some power in utilizing these neural network quantum state. Or we can think about not just neural network, but also like say tensor network and others. One of the application here is that we can think of the lab state as the thing that was fixed. And then we have our target state that was changing using machine learning models. So we train them. And basically what we could do is we can use the shadow overlap as a loss function to test between the model that we are changing and the lab state that is fixed. And hence, by using shadow overlap, we will be able to train these models. And furthermore, not only we can train them, after training, we can also just look at the shadow overlap and see that if it's close to 1 or not. If it's close to 1, then we know that the machine learning model has done well. We can certify it and guarantee that the prediction from the ML model will be correct. Otherwise, a lot of times, these neural quantum state has this problem, which is it can often hallucinate things. Like it's thought it's learning certain things, certain pattern, but actually it's not there. And when you use it to do prediction, it can just be very wrong. So by having this certification protocol for ML models, it helps in providing rigorous guarantee to the prediction of the ML model. So just to showcase that, I'm going to consider training some neural network. So just for a recap, a neural quantum state is a classical neural network that takes in a bit string B and produces the probability amplitude for that bit string. And essentially, one would just like parameterize it and train them. But here we're going to consider a slight modification of it, which is easier to train for this shadow overlap case, because shadow overlap always look at like pairs of bit string. So instead of the standard one, we're going to consider like this modified neural quantum state, where we're given 2 bit string, B0 and B1, and the neural network would predict the ratio between them. And note that this also represents the state psi, because we can query the neural network n times and multiply the ratio to create the probability amplitude for any bit string B. And what we're going to consider is we're going to consider some 120 qubit state with kind of nominally exponentially high circuit complexity, because we can play with this trick of lazy evaluation that was often used in like random function literatures to simulate exponentially high circuit complexity states. And these states, they're essentially very high design state. So they have volume law entanglement, and hence the ground truth for the purity will decay exponentially. So if you look at subsystem parity, like half-chain subsystem parity, the purity will decay exponentially, and then only when we start to include the whole chain, it will start to go back up. And when we randomly initialize the neural quantum state, there's actually no entanglement in it, and hence like almost no entanglement in it, and hence the purity is very close to 1. And now what we can do is we can train these neural networks using this shadow overlap based loss function, and then certify using shadow overlap again. So here is just like the training dynamics of the neural network. As we start to train, the loss function goes down, and the shadow overlap start to go up. And at the end, it's very close to 1.0. And we can also kind of, because it's simulation, so we can also test the fidelity, and we see that the fidelity is also very close to 1. And now we can make sure that the neural network that we trained is actually correct, and it will produce the right prediction. And that's indeed what we see when we ask it to predict the purity, the subsystem purity. We see that it accurately tracks the ground truth up to some fluctuation, because neural network quantum state, when you try to use it to do prediction, it's based on this multicausal sampling method that have its intrinsic statistical error. That's the second application. And there's a third one, which is we can use it to optimize circuit. So let's say the goal now is to prepare some target state psi by optimizing some quantum circuit, like a parameterized circuit or some discrete circuit. And one way to do that is now we can utilize this shadow overlap again, because we can just do some measurement on the output of the circuit and test its shadow overlap with the target state. And then we try to maximize the shadow overlap such that the circuit actually produces the desired target state. And here's an example for if you're trying to construct some n-qubit MPS using Hadamard, CZ, and T gates. Let's say we have a sequence of ways to construct the MPS, and then now we just keep applying the sequence of gates in order to try to construct them. And here the plot just showcases how the fidelity and shadow overlap changes when we add in one gate at a time. So from 0 to the final number of gates. And we see that for small system size, both just keep increasing. But when we look at like much bigger system size, like 50 qubit, we see that shadow overlap, when we start adding in gates because of its Hamming distance behavior, it starts to grow already at the beginning. On the other hand, fidelity has this very barren plateau-like behavior. So when we start to add in gates, the fidelity keeps becoming 0 because we're not that close. There's still a few qubits that are very far away. And only at the very end, it starts to shoot up, which means that when we try to train these circuits using fidelity, it's going to fail. That's like a well-known thing in the study of quantum neural networks. On the other hand, when we use shadow overlap, because of its nice structure, we can actually train it very easily.
How does this behave if you train with like the local fidelity? And is the, I guess that relatedly, is the shadow overlap a close cousin of the average local fidelity?
Yeah, so local fidelity still requires, local fidelity is this. It's like if we have a target state in mind, and let's say unitary U generates the target state, then local fidelity is defined by first applying U dagger and then measuring each qubit and checking whether it's 0. So note that the definition of local fidelity still requires running a deep circuit, whereas shadow overlap does not. So in a way, one can think about it as like a cheap single qubit measurement-based version of local fidelity. But at the same time, we're not entirely sure if, like, I think they share a lot of feature, but, and one could think of shadow overlap really as like a cheap version of it because it only requires single qubit measurement, not these like entangling circuit. But I think there are also cases where they differ. So the relation between the two is not so clear.
Yeah, actually, this looks amazing, especially on the right. My question is, why does it work at all if you use fidelity? The state construction step all the way up to 40, it doesn't change.
Yeah.
Suddenly, how does it actually,
Oh, because you start, I mean, at the very end, like I'm thinking of it, sorry, here I'm considering a sequence of gates such that when I run it, it actually creates a target state. So there's no training involved or an optimization. This is just like,
so it's not optimization step.
Yeah, no.
It's more like,
I'm just considering the actual circuit.
And then like partially
Yes.
not. Okay.
Yes, the optimization is shown here. And basically, if you train with fidelity, the fidelity just maintains 0. Whereas if you train with shadow overlap, the fidelity maintains 0 and then shoots up. On the other hand, on the shadow overlap side, when you train with fidelity, you see that it's just random walking on the barren plateau. And hence, like it's still moving, like the shadow overlap fluctuates. But then if you train it with fidelity, it's not going to show signal. So it's not convergent. And on the other hand, the shadow overlap just slowly grows, and at the end, it converges. So yeah, so these are a few of the applications that we thought of for this new certification protocol. And to conclude, we proved that almost all quantum states can be efficiently certified from few single qubit measurement. As we know, like this is not, like we want something maybe even more ambitious. Can we show that all quantum states can be efficiently certified from single qubit measurement? It seems a little bit unclear if that should be true. So maybe we can aim for another open question, which is, can we cook up state so that we can prove that such state cannot be certified using few single qubit measurements? So for example, like GHZ, it can be certified using single qubit measurement. And a lot of the other examples that we look at, like Tori code or some other quantum error correction codes, they all can be certified using single qubit measurement by considering some more advanced version of our protocol. So yeah, so in a way, we still cannot find such a state that cannot be certified, which if the answer to this is no, there are no such states, that would be a good thing because it says all quantum states can be certified with few single qubit measurement. But that's an open question for people to think about.
So for the final question, how do you look those same to spin liquid, or would that be?
Yeah, that's also like that.
Okay.
Yeah.
That can be certified.
I think so. Yeah.
You looked at it, or?
I mean, in a way, this is like variants of Tori code, and I think the way to certify Tori code can translate to spin liquids. But I haven't looked at, for example, like LDPC codes or some other weird codes, or if we embed codes inside codes and so on.
Yesterday, someone was telling us about these projected ensembles, and this looks a lot like.
Yes, it is inspired by projected.
I guess, okay, so I have 2 questions regarding this. First, is this relaxation condition related to the universality that you were talking about?
That'd be fun to look at.
Yeah, that would be fun to look at.
And second, can you go to like higher dimensional simplices and get better estimators somehow?
Yes. So there are versions of it where instead of being just, I guess you mean like instead of Boolean hypercube, you have more connection.
Go to like a face and then
Yeah. I think one can essentially, like if you, for example, measure a few qubit in some entangling basis or a few qubit in a random Pauli basis, that creates like highways on this.
So, if I understand correctly, there is a qualifier to the statement that you need to be able to represent the state or compute it efficiently classically. Otherwise, you can't serve it. Right?
Yeah, we need to be able to calculate this 1 qubit ideal.
Yeah, but out of the original highly entangled state.
Yes. So it could still be like, for example, a lot of like pseudo-random state, like random binary phase states, they are efficient and computable, and yet they're still highly entangled. They're indistinguishable from R and so on.
So how it is actually the computation of your shadow overlap, in particular, for example, compared to the XCB?
It's the same.
Okay.
It's the same as XCB. Like
you showed that before how to do them.
I see. Yeah, I could quickly go back, but it's the same as XCB. Like the computational costs of this and XCB are, one can think of it basically exactly the same. So like in XCB, you need to be able to estimate like the probability, which are like the absolute value of these guys. And here we just need to estimate the probability amplitude. So they're essentially the same.
Yeah, can you go one slide before the conclusions?
Yes.
Oh, perfect. Yes. One more.
Oh, this one.
Thank you. So for example number 2, this looks very close to neural shadow quantum state tomography, right? So there are 2 versions of neural shadow quantum state tomography, one with Clifford tail, but one with the poly shadow, which has only local measurements.
Yes.
So where also one has an ansatz and
Yes.
one really evaluates the overlap using the shadows and not the cross-entropy. So do you want to comment of how the 2 relate?
So for example, you can take randomized Pauli measurement and try to train a neural network. But then, yeah. But then in that case, you don't have, I think the main thing for using the shadow overlap is that it also gives you certification from single-qubit measurement, which previously we don't know.
The scheme is very similar, but the certification is
Yes. The scheme is very similar. Like the thing you do on measurement side and so on are very similar. The only difference is really like, because of the theory that we proved, at the end we get the certification that the ML model that was trained well, like get a good shadow overlap score, it is also really close to the actual thing. So that's the main thing that was missing from previous works.
How do you? I didn't understand. How do you actually do these like 1 qubit estimations efficiently?
Oh, so yeah, you mean like how do I get this probability amplitude for some bit string that I got out?
Yeah, like it's random, right? So how are you?
Yeah. So I mean that's like, so that's like, for example, the same as in cross-entropy benchmarking. They also need to estimate these kind of objects. So I mean,
it's not like necessarily efficient, just given.
It's not necessarily efficient.
So you don't. There is no efficient procedure for computation. This is not computationally efficient.
In general, yeah. In general, if you have a weird state psi, then this is not computationally efficient. But if you have psi that can be represented by a neural network or a tensor network or some other
if I have a
representation.
quantum circuit for psi, is it efficient?
No, it's not. No.
Okay, I would actually suggest, in view of time, perhaps to postpone the other remaining questions to the lunch break. But still, I mean, I think you deserve an applause by all of us. Thank you very much, Rob.